The conservation of total mass is a general principle that is valid in virtually all circumstances. To solve any problem mathematically, the number of equations must be equal to the number of unknowns. The total mass balance is often required along with other relationships to produce the complete solution. We learned about the theory of material balances through simple, intuitive examples in our previous video. The solution to the question posed in that video is also available now. Today, we will learn about the real-life applications of those concepts and go over a step-by-step solution strategy that can be applied to any material balance problem. Mass flow rates are a key part of material balances. Mass and its flow can be represented through several different expressions. Let's look at a few examples. In a candy dispenser, the mass flow rate can simply be the mass of each candy multiplied by the number of candies being dispensed. For water in a measuring cylinder, we can calculate mass as density multiplied by the volume and mass flow rate as density multiplied by the rate of change of the volume, also called the volumetric flow rate. Alternatively, we can use the molar weight multiplied by the number of moles or the rate of change in the number of moles to calculate the mass and the mass flow rate respectively. If we are working with mixtures, we can use concentration to calculate the associated mass. Concentration is a relationship between the quantity of one component and the quantity of the other components or the whole mixture. To obtain the mass of one component from its concentration, we multiply it by the known total quantity of the other components or the whole mixture and then convert it to units of mass using the relationships we practiced earlier. For example, if we want to calculate the mass of cornflakes in a bowl of milk, when the concentration is given in number of flakes per liter of milk, we multiply the concentration by the volume of milk in the bowl in liters to obtain the total number of flakes in the bowl. And then, we multiply the number of flakes by the mass of one flake to obtain the total mass of cornflakes in the bowl. You can save this table of all the different ways to express mass flow rates in terms of the known information. We cannot discuss all of these expressions in this video, but let us know in the comments if you want to see this table explained in detail in a different video. And remember, whenever we are working with composition fractions or percentages, we can write an additional equation where all the fractions sum up to 1. Now, how do we decide which representation of mass we should use? It all depends on the problem we are given. We can even use different mass representations for different species or different terms. For example, we can write the equation for the simple scenario of water flowing through a pipe using all these different ways. The important thing to keep in mind here is that all the terms in the equation should finally have the same unit of mass. Substituting the values along with the units in the equation shows that this is not the case here. If we have one term in grams, the other in kilograms, and another in ounces, we need to use conversion factors to fix that so that all the terms have the same unit. Consider the example we studied in the previous video, pedestrians and cars crossing a bridge. What are the different ways in which we can express the flow of mass in this example? Let us know in the comments. The basis we select defines the scale of our calculations. A basis is an assumed reference quantity for our system used to simplify calculations. We are not saying this is the actual quantity in real life, just what we are going to base our calculations on. For example, if only concentrations are known but not the flow rates, we can choose a convenient basis like 100 kilograms of input material or 1 mole of output material. This often simplifies percentage or mole fraction calculations. We can also choose a time basis depending on convenience and the provided information. In our water pipe example from earlier, we can evaluate the system over a second, a minute, or even an hour. We can select the basis to match the provided system constraints, like a single batch as the basis for a batch process, for example, cooking one batch of rice. Even for a continuous process, like the water pipe problem, we can consider one bottle or one bucket being filled up as a single batch of the process. There can be multiple choices for the basis of a problem, but we must ensure that the basis is consistent throughout the calculations. After solving the material balance on our chosen basis, we can scale up or down to match any requirements for the final solution. Real systems often involve material transformations. When a material changes its form in some way, like ice melting to form water or wood burning to form ash, we call it a transformation. The transformations may either be physical or chemical in nature. In a physical transformation, the molecules of the material stay intact. The same material exists in multiple forms, and the law of conservation of mass holds true for each type of molecule and also for each form of the material. Whereas, in a chemical transformation, the molecules of the material change their identity. So, multiple materials of distinct molecular identity exist during the transformation. But what maintains its identity is the atom. So the law of conservation of mass holds true for each type of atom. Now, if we are representing mass using moles, we use moles of molecules for physical transformation and moles of atoms for chemical transformations. If we are dealing with multiple materials or multiple forms of a material, we are naturally working with multi-component systems. If material A transforms into material B, meaning material A is consumed in a transformation to produce material B, material A and material B are two different components in the system. But where do transformations fit in our material balance equations? Let's look at the multi-component mass balance equation. For any component I in the system, all mass of I entering the system will either accumulate in the system or leave the system. In better words, all mass of I being added to the system will either remain contained in the system or get removed from the system. In the transformation of material A to material B, material A is being removed from the system as the transformation consumes it, and material B is being added to the system as the transformation produces it. The mass being consumed and the mass undergoing formation are part of the mass being removed and mass being added, respectively. When we include the transformation in our material balance equation, we get the complete mass balance equation for a multi-component system with material transformation. Mass of component entering the system plus mass of component being formed in the system minus the mass of component accumulating in the system is equal to the mass of component leaving the system plus the mass of component being consumed in the system. If we take the time derivative of this equation, we get the relationship between mass flow rates. Applying the steady state condition, we get the steady state mass balance equation for a multi-component system with material transformation. The rate of mass of component entering the system plus the rate of mass of component being formed in the system is equal to the rate of mass of component leaving the system plus the rate of mass of component being consumed in the system. Based on the transformation, we may see the use of different words like these. We simply need to correctly associate them with mass formation or mass consumption and write them on the correct side of the material balance equation. We may also need to use the provided information like stoichiometry, selectivity, or conversion to obtain additional relationships to calculate these terms. For example, if 1 unit of A transforms into 2 units of B with 40% conversion, the steady-state material balance equation for A will be written as mass of A entering the system is equal to mass of A leaving the system plus mass of A being consumed, or mass of A entering the system is equal to mass of A leaving the system plus mass of A entering the system multiplied by its conversion. Using the same principle for B, we get mass of B being formed is equal to the mass of B leaving the system, or 2 times the mass of A being consumed is equal to the mass of B leaving the system. We now have all the tools we need to start solving real material balance problems. Let's put together a step-by-step strategy. First, we read the problem to understand the setup and the requirements. Then, we draw a diagram representing the system and mark all the known information about the mass inputs, outputs, and the accumulations. Select a suitable basis, then start writing the material balance equation algebraically for the total system and for each component. If we want to analyze what is happening during a process as it proceeds, we use the mass flow rate balance. If we are more concerned with the result at the end, after the process has finished, we want to use the total mass balance. Both sets of equations are valid across both continuing and completed processes. It's just a matter of what is more useful. Figure out which of the quantities are known or computable with the known information and which quantities are unknown. Pre-fill any unknown quantities based on reasonable assumptions if possible. For example, we can assume the density of water to be 1 kg per meter cube if the density or temperature is not specified in the problem. Rewrite all the mass terms using the appropriate mass representation as we learned earlier. Substitute the numerical values along with the units. Now, ensure that all units are correct and consistent. Apply any conversion factors if needed. Finally, calculate the unknown quantities. Depending on the problem requirements and the basis we selected, we might need to scale our calculated quantities to obtain the final desired solution. Today we have learned how to apply the material balance theory and law of conservation of mass to real-life situations. We have devised a step-by-step solution strategy covering all aspects and variations of problems. In the next part, we will solve some sample problems to see the strategy in practice. Till then, you can try applying it on textbook problems or self-constructed examples. Be creative. Let us know if you come up with an interesting problem or if you come across a problem you are unable to solve, and we will try to include them in our practice problems next time. If you have any questions, ask us in the comments. If you found this video helpful, hit the like button. Stay tuned for the next part and don't forget to subscribe to Exemplify.